this little article from the World Resources Institute. We always talk about hyper-local predictions, early warnings that we need, because all global warming is local and all the impacts are often hyper-local. And this also applies to heat metrics. There are often not the same heat wave definition used, even though you hear about heat waves in Europe, heat waves in Northwest India, in South India, which can have very different levels of humidity and so on. So this is just a nice article that puts together the story of why it's important to have location-specific heat metrics to drive proper decisions on managing the heat waves and disasters, impacts of those heat waves on outdoor workers, old people, young people, businesses, and so on. So this says beyond the thermometer, 5 heat metrics that drive better decision making. It's a bit of a long text, but I'll read it just because the points are very good. The way scientists and policymakers measure heat as they seek to combat rising temperatures across the world's cities require more nuance than just looking at the daily outdoor temperature. There are a variety of tools that can help show a more complete picture in terms of what people experience and in a given location. Cannot be a large scale, because what people experience in a coastal heat wave versus a mountain heat wave, urban heat wave, could all be very different. Some measurements like land surface temperatures can help compare different parts of a city. Others like air temperature, heat index, or wet bulb globe temperature describe the regional conditions across a neighborhood or even an urban area. Wet bulb globe temperature is of course not just the wet bulb temperature, because it also accounts for factors that control the wet bulb temperature, like heat, shade, direct sun versus shade, and so on. So it's more complete. Increasingly, experts look to more complex data known as the thermal comfort indices to show the impacts on people where they live. And many countries, Singapore, European countries, they are doing more and more work on individual thermal comfort indices as well. But when you want to make a decision for a neighborhood or a city, you have to worry about some kind of average thermal comfort and also heat metric. After 2024 was recorded as the hottest year on record, researchers project a nearly 3 degree Fahrenheit rise, so let's not worry about 2100. But this kind of an warming, any level of warming, is going to disproportionately impact urban centers. They already contribute disproportionately to climate change, and they feel disproportionately more impacts from climate change as well. So adding another degree of warming, and it will expose 4 billion more people who will live there. So there are projections on how urbanization will continue and how more and more people will be exposed to heat. And with humidity, heat, warmer temperature is a thirsty warmer atmosphere is a thirsty atmosphere. It will hold more moisture, so moisture is always a deadly combination with warm temperatures. As part of the global weather extreme system, heat can span across broad geographic area, but individuals experience it at very local scales. Obviously, choosing the best metric to measure a desired outcome appropriately will be critical for cities worldwide to effectively address the challenge of urban extreme heat as temperatures continue to rise. So traditional ways of measuring heat have been that when we talk about heat exposure, we are referring to a series of different heat sources that make someone feel hot. Suppose a person stands outside during a heat wave. Direct radiation from the sun, reflected radiation from the surfaces like roads or buildings, ambient air and moisture in the air, all can contribute to how hot that person can feel. Okay, so here are some environmental variables that matter: ambient temperature, humidity, solar radiation versus shade, airflow, whether there is a breeze or not, and there are more complexities in terms of using a fan, for example. So it can, it's very tempting to always turn on the fan when it's hot, but there are some studies showing that it can actually have counterintuitive effects. Radiant heat, so imagine that you are wearing warm clothes and your body is unable to get rid of the heat. So that's thermal radiation going out of the body that can be trapped and make you warmer. And there is reflected radiation, as we said, from buildings and roads and so on. Here are a few of the additional heat metrics and their uses with their limitations. So let's, land surface temperature, so obviously is calculated using various platforms, and they can be surfaces or rooftops, treetops, roads, etc. They are all referred to as LST. LST doesn't mean much to the everyday person, however, because it's easy. Land surface temperature is LST. LST is easy to measure, but researchers use it for scientific heat mapping, and for many years have considered it the go-to for urban heat analysis. You remember UHI, the urban heat island effect that we discuss a lot. LST is useful in comparing different parts of the cities and evaluating which surfaces are likely to absorb heat and slowly re-radiate it throughout the day and night. However, LST isn't helpful for understanding people's heat exposure because it doesn't account for most of the ways that humans experience heat. So even if a person is standing on cool grass, they will feel hot if they are in the sun on a warm, humid day as opposed to the shade. Right, just a small difference. And if humidity is low, then it can be several degrees cooler in the shade compared to direct sun. Air temperature, on the other hand, measures temperature of the air about 2 meters above the ground as a standard metric. Because it's easily modeled and understood, air temperature is the measure local news organizations and other outlets tend to use in their reporting. It's measured with a simple thermometer and gives clear picture of a location's ambient weather condition minus any other factors like humidity or direct sunlight that might make a person feel hot, so you have to account for them. Because air temperatures look at the background conditions, air temperature is an ideal metric for analyzing and comparing temperatures across time as well. Across neighborhood or city, though, air temperatures can be difficult to measure. Consistent measurements over a wide area rely on weather stations, which can be geographically sparse and expensive to maintain, and on low-cost sensors, which can be faulty and prone to breaking. So I'm having a hiccup, somebody is remembering me. But anyway, you understand that data sparsity can obviously be an issue even if you just rely on simple air temperature as a metric. However, air temperature doesn't capture other atmospheric or environmental factors like the number of trees that provide shade that can affect how hot a person might feel in a particular area or neighborhood. So greenery can, I live on a nice campus, I'm leaving tomorrow, but still most campuses, educational campuses, have lots of tree cover compared to just outside the gate, and when you walk in and out you can feel the difference very quickly as well. So it would take something really big like a body of water or an entire neighborhood of cool roofs to significantly affect the air temperature of an area of a certain scale. So if cities want to address the impacts of local heat exposure, air temperature would not provide enough specificity to inform human scale interventions designed to protect people's health. There are adaptation measures like cool roofs, even paints that are wavelength specific and so on, that are now being used to cool larger areas, but it still needs additional metrics for human thermal comfort as well. Heat index and wet bulb glow temperature. Meteorologists calculate the temperature, what the temperature feels like, using the heat index, a metric that adjusts air temperature based on humidity. For example, when humidity and temperature are high, the body has a harder time regulating its temperature through perspiration, because perspiration, the latent heat loss, depends on the humidity gradient. It's not just sensible heat. So you then, if the air is very saturated with humidity, then the ability of the body to get rid of the heat we are sweating the air, evaporating the sweat is going to be decreased. This is why we worry about wet bulb temperature, because even though a temperature that one can tolerate may be high, the wet bulb temperature at which body begins to lose its ability to lose heat through evaporation is much lower, so you have to worry about that. So in contrast, low humidity at a high temperature, often called dry heat, would feel cooler because low moisture in the air leads to faster evaporation of sweat, which cools down the body. Heat index can therefore predict how the body will react to weather on a given day, making it a helpful tool for determining if it's safe to work outdoors or play sports. Especially when you put kids out, you need to know these kind of details. Wet bulb glow temperature is a similar metric, but it considers direct sunlight and wind speed in addition to air temperature and humidity. This metric can provide additional insight into heat exposure by determining how much hotter a person feels in the sun and with limited breeze. Heat index and WBGT are measured with special thermometers or weather stations and interpolated like air temperatures. Given that both these measurements account for more variable heat source, heat index and WBGT are better indications of heat load, the cumulative impact of heat from the environment on a person, than temperature alone. Seem obvious, but we need to still discuss them so that metrics take into account these details to facilitate better decisions on managing heat waves, right? But just like air temperature, these also don't vary much across space and therefore cannot always account for changes across the local environment. Here is a prop showing a man cooling himself under a water spray in Krakow, Poland. Traditional methods for measuring heat don't always take into account how much heat people can feel on a hot day. So you have to be very careful about the particular metric you are using, especially to make decisions. These traditional methods often used to measure heat sources do not describe all the dimensions of how people feel heat or its impact on their health, which can vary widely from person to person, also on dependent on gender, age, etc. Environment, for example, plays a significant role and can change the impact even within a single city or even a neighborhood. Residents of downtown LA, Los Angeles, with its crowded city blocks and lack of green space, will experience heat differently than those on the west side of the city, who might benefit from the cooling effects of the Pacific Ocean. The sea breeze may bring drier, cooler air because the upwelling and cooler temperatures along the Pacific west coast of the US. Each heat measurement has utility and can inform different interventions, from cool roofs to early warning heat alert systems. However, these traditional methods of measuring heat don't account for the full scope of how heat affects people in their neighborhoods. For city officials to ensure their interventions adequately address the growing impacts of extreme urban heat, cities should also use thermal comfort modeling. This is tricky. As I said, you can do that, people literally instrument bodies and have them walk in the real world, in the lab, etc., to see thermal comforts. But how do you translate that to managing heat for a population, right? Measuring heat with thermal comfort modeling. When someone stands outside on a hot day, direct radiation from the sun, reflected radiation from surfaces, ambient air temperature, wind level, and humidity all simultaneously affect them. Thermal comfort metrics calculate the cumulative effects of these collective heat sources, providing our most detailed assessment of human heat exposure. Typically, you do it at an individual level. If, for example, a person walks down an asphalt street with partial shade coverage from trees at noon on a hot, humid day, thermal comfort metrics provide a sense of their heat exposure, combining factors such as sunshine filtering through the tree canopy, the hot asphalt below their feet, and the weather around them. If the person walks back along the same street at 6 p.m., a thermal comfort metric can predict that they will feel cooler because of the longer shadows and lower air temperatures, even if the heat from the asphalt may have increased during the day. Thermal comfort is measured using a set of instruments, including specialized thermometers and a wind meter, but more frequently, it is calculated using three-dimensional models that consider meteorology, direct and reflected radiation, tree canopy, buildings, land use, and shade. Scientists increasingly use metrics like the Universal Thermal Comfort Index, mean radiant temperature, or physiological equivalent temperature to calculate thermal comfort. Singapore, which I mentioned before, for instance, planners may model thermal comfort to pilot urban design interventions that reduce heat exposure, including wind corridors, green buildings, and shade that can cool the spaces where people feel the hottest. So they are taking these measurements and converting them into urban design. It's a nice, small, rich, homogeneous, well, it's not so homogeneous, but it's relatively small, run like a nice family business, so they can make decisions at these levels, but it's not possible when you have monstrous mega cities like Mumbai or Beijing or Shanghai and so on. Thermal comfort metrics are calculated at very local scales in radiuses between 1 and 5 meters, which capture variations in shade, vegetation, surfaces, and other relevant aspects of a city's design. So you want to know all the gradients. As a result, thermal comfort indices help scientists not only to understand individuals' heat exposure, but also heat resilient infrastructure that could potentially mitigate that exposure. Modeled metrics are also useful in prioritizing and locating interventions because thermal comfort metrics use modeling. They can show the local effects of constructing a new park, planting trees, or orienting buildings to avoid shade to pedestrians. Now there are also digital twins used to try these scenarios on the computer before you implement them for effective and efficient use of the money for doing these things. Modeled air temperature can similarly inform the impacts of scaling interventions like cool roofs across a whole city. So here is sorry about that, a prop on how heat can be measured and modeled in multiple ways. So land surface temperature, which is looking at the radiant heat coming from the top, from the bottom, sorry, and it can be mapped easily with the satellite and so on, but how useful is it? Air temperature also can be easily measured and mapped with in situ and satellite remote sensing instruments. So that's ambient temperature, what a person feels. But a heat index then also has to take ambient temperature as well as humidity. But if you want to go towards wet bulb globe temperature, then you also consider solar radiation, ambient temperature, wind, humidity, and so on. But if you want to go further and use Universal Thermal Comfort Index UTCI, then you use radiation, ambient temperature, humidity, airflow, as well as radiant heat and reflected and radiant heats. Sorry. Okay. So in recent years, improved high resolution data availability around the world has made it possible to calculate thermal comfort modeling more accurately and cheaply, making these metrics feasible to use alongside traditional methods. Now, scientists and policymakers have more options when assessing extreme heat. They can choose the right indicator, physical scale, and time period to look at how the city affects how hot people get and how hot they feel. So matching the right metric to local heat goals then becomes very critical. As temperatures continue to rise in cities worldwide, interventions to mitigate extreme heat will become increasingly important. Using the right metric to evaluate the impact of these interventions is critical in considering how, where, and when the changes will be effective. So with global warming, warming will not be uniform, but even when, for example, India is not warming as fast or even cooling, 2023 was a very warm year, but India actually had cooler year, but heat waves don't go away. So mean temperatures and heat waves are not always directly related. Mean temperature can go down, but heat waves can go up because of the way global warming works. It's not all local, right? Different stakeholders have varied goals related to heat. As they plan for more heat resilient cities with better infrastructure and co-benefits for cooling across sectors, they should select appropriate metrics for measuring and informing those goals. Some policies and projects will focus on protecting human health during heat events, while others might prioritize reducing the formation of ground level ozone, which can exacerbate heat impacts, or lowering burdens on energy grids. Each goal depends on a different kind of heat metrics and data to help plan and prioritize its implementation. So here are some potential heat related goals and tracking metrics. So here are the goals, metrics to inform the implementation, and this just continues along the same way. So lower citywide temperatures, so you go for air temperature, protect pedestrians outdoors, thermal comfort indices, set safety limits on outdoor activities, so use heat index, wet bulb globe temperature, and if you want to if you want to keep people cool in transit stops or public spots, then you use thermal comfort indices as well. Reduce indoor heat exposure and energy use as a goal would require you to use air temperature, land surface temperatures, temperatures of roofs, and so on. If you want to reduce the formation of ground level ozone, then you want to track air temperature as a heat metric as well. So entire cities experience heat, but so do individuals. So city officials should consider heat interventions that target heat at a citywide scale to move the needle on ambient outdoor temperatures, while also prioritizing local to neighborhood scale change to impact people's day-to-day heat experience. There are also time scales. Over time, you want to make sure that your measures are keeping the city cooler, reducing the urban heat island effects, and then managing crisis of a heat wave as well at neighborhood scales and individual scales. Just as different metrics are appropriate for different goals, the same is true for metrics which are measuring the effectiveness of different interventions. For example, cool roofs reduce heat across a neighborhood, so their effect is best measured by looking at regional air temperatures, shade protects individuals by lowering their heat exposure, and so it can be best understood through thermal comfort metrics. Also, when we are talking about cool roofs, we have to worry about, let's say, mid-latitudes. Europe is experiencing lots of heat waves, but they also have winter to worry about. So if you implement vast measures on cool roofs, what does it mean for winter? Can it reduce temperatures significantly in the winter as well? Will that mean there will be increases in energy used for heating? So all those details are not considered here. We are just focusing on mitigating heat and preparing for increasing background chronic changes in temperature as well as heat waves as acute stressors. Okay. As the risks of extreme heat continue to intensify in cities, leaders and policymakers need a diverse set of tools to understand and respond to risks. Simply knowing that it's hot in a city is not enough at all. Choosing the right metric for each dimension of the heat problem can point policymakers and residents toward deeper knowledge of their local challenges and potential solutions. Okay, so it's a nice short article, summarizes the ideas very nicely, and these are very critical for managing crisis at heat wave time scales, as well as building adaptation measures and resilience to heat, and minimizing heat indices and chronic heat changes. Okay, let's leave it here.